Hi, I'm Prajwal. I'm going to be presenting our work on weekly supervised finger spelling recognition in British Sign Language videos. This is a joint work with Hannah Bull, Lilian Momeni, Samuel Albany, Gul Varol, and Andrew Zimmerman. Our goal in this work is to automatically detect and recognize the fingerspell sequence of letters in British Sign Language. An example of finger spelling corresponding to the word panda is shown below. Let us check out the same clip again but in slow motion so that we can spot each letter. We have P, A, N, D, and A. We can see that the task is quite challenging. So what are the challenges? The first challenge is that the fingerspell letters look very similar. You can see here the difference between A and I comes down to touching the index finger or the middle finger. The second challenge is the occlusion of the two hands. Here we see an example of the word love with almost all the letters being entirely occluded. So in order to recognize these letters, we need to look beyond the exact frames where the letters are fingerspelled and instead look at the transitionary frames between these letters for cues. Finally, it is important to note that not all letters of the word need to be fingerspelled. In the example shown here, the signer only fingerspells an N for the word Nottingham. Lastly, there are no datasets for this task. Any sort of manual annotation is challenging, time-consuming, and quite expensive in terms of both time and money. Incidentally, BSL is particularly more challenging than sign language datasets like American Sign Language that use only one hand for finger spelling. And because of that, they avoid some of the problems which we mentioned previously, such as the occlusion problem. Our work tackles these challenges with the following contributions. We train a fingerspelling detection and recognition network that learns from noisy automatic annotations with weak supervision. In order to handle the noise in our training data, propose a new loss function and also make use of pseudo labeling to improve the recognition accuracy. Finally, we released the first benchmark on British Sign Language fingerspelling with about 5K manually verified fingerspelling clips. We evaluate our models on this test set and make all the annotations public to encourage future research in this space. Let us now delve deeper into each of these subparts. Starting with our model, we propose a joint architecture that can perform three tasks. Given a sign language clip, we would like to know if there is any fingerspelling instance within this clip. If so, we want to know at what times it is happening. And finally, we want to recognize what is being fingerspelled. Our transpeller architecture outputs all these three outputs using three heads. To give you an overview, we start by extracting the visual features for each frame using a visual front end, which is a pre-trained video Sven model on sign classification. We project the features using a fully connected layer and add the temporal position encodings. This feature sequence, along with the learnable CLS token, is processed by a transformer encoder. At the CLS time step, we make a binary prediction of whether the input segment contains fingerspelling or not. At each frame, we make another binary prediction indicating whether this frame contains fingerspelling. This allows us to localize the fingerspelling in time. Finally, we also have another head that outputs a softmax probability over the English characters to transcribe what is being fingerspelled. You can find more details about this in the paper. Our transpeller model is fully trained on automatic annotations. These automatic annotations are fingerspelling detections with word labels and what is being fingerspelled. To get these annotations, we have two steps. We start with nearly 1,000 hours of BobSL training videos, in which we would like to first detect clips which contain fingerspelling. To do this, as you can see on the left, we take about 100 exemplar frames that we manually verify that they contain fingerspelling. After extracting the per frame features of the video which we want to annotate, we construct the cosine similarity score maps between the fingerspelling video and each of the exemplar frames. For each video and exemplar image pair, we get a 1D vector of size t cross 1, t being the number of frames in the video. Locations with maximum score indicate the location of the finger spelling. Now, given these detections, we need to associate them with word labels. To do this, we use a visual keyword spotting model and see if the signer mouths any word from the subtitles surrounding the given signing clip. If we find high confidence mouthings that overlap with the finger spelling detections, then we have a word label for that finger spelling instance. Now, clearly, since these annotations are automatically obtained, there is bound to be noise in the training data. So we employ two strategies to counter this and improve our performance. One, being a new loss function. The other is to do a multi-stage training after a round of pseudo labeling. Let us look into the first one now. We propose a new loss function called the multiple hypothesis CTC loss, which is built on the observation that if a word annotation is incorrect, then the correct word annotation is likely to be a surrounding noun in the same subtitle. So during training, what we do is, given the model's predictions for an input clip, that is MOY, in the example we show here, we compute the CTC loss with the prediction and all the nouns in the subtitle and simply choose the word that gives us the lowest loss as our target ground truth. The second strategy is pseudo labeling. After training a model with the initial set of annotations, we can use it to do a round of pseudo labeling of our training data. This gives us more finger spelling instances, better localization, and better word labels. Let us check out three cases on how this helps. If you recall, we mentioned that we use mouthing cues to associate finger spelling detections with words from the subtitle. But what if two nouns are mouthed very close in time and only one of them is fingerspelled? Here, because the word Holmes overlaps with the fingerspelling detection of Berkeley, we get a wrong label. But a model, after training on the initial set of annotations, predicts the characters BERUY. Using a modified version of the edit distance, we associate this word to the word Berkeley. A second case if multiple nouns are mouthed, but only some of them are fingerspelled. Here, Inspector John Rebus is mouthed, but only John Rebus is fingerspelled. As you can see, the model that we trained on the initial set of annotations only predicts JHNRBUS, which tells us to remove the word inspector from the annotation, thus giving us the correct word. Finally, the mouthing model can simply fail to detect certain mouthings. Here, Simon is simply not detected at all. So essentially, you're missing out on a training sample. So after pseudo labeling, we can even get new training samples because the initial model would predict characters which is corresponding to the word Simon in the subtitle, and we can annotate instances that were not annotated before. So to recap, we have over 1,000 hours of continuous British Sign Language video data in the Bob Russell dataset. Using a small set of exemplars, we detect fingerspelling instances and associate them with word labels using mouthing cues. We get about 59K training samples, which we use to train a model on these annotations and perform a round of pseudo labeling, which gives us more detections and more word labels for further training. We get about 111K clips using which we train a final model. All of the training annotations are automatically obtained and can contain label noise. But for benchmarking the performance of a model, we manually annotate 5K fingerspelling clips from the Bob Russell test set. We report character error rates on the manually verified test set. So here, a low character rate indicates a better performance. At the model trained on the initial set of annotations, we get a high character rate of close to 58, but we progressively improve this by using MHCTC. The rate drops further. After pseudo labeling, we retrain our models and get large boosts in character rates. We can see that our novel multiple hypothesis CTC loss and the pseudo labeling steps, both of them clearly help in boosting the performance. Let us look at some test results. Here we recognize the letters in Mumbai. You can see that not all letters are distinctly fingerspelled. The task is clearly quite challenging. This is a second example. Here we get most letters, but mistake the letters O and E, which is a common error because of how similar the corresponding signs look perceptually. This is an example where we can see that the fingerspelled characters need not be single words, which becomes more challenging for a model. And finally, this is an example showing that the fingerspelling need not only be proper nouns, many common nouns can also be fingerspelled. And here is a collection of many results just put together. A test set and models will be released to support future research on this topic. Thank you for your attention.